Welcome all. In this video, I will discuss UV visible spectroscopy. Different topics under UV visible spectroscopy are chromophores, oxochromes, electronic transitions, Beer-Lambert's law, derivation and deviations, instrumentation, and applications of UV visible spectroscopy. This includes single component and multi-component analysis. Chromophore. Chromophore is part of the molecule which is responsible for imparting color. So which groups are responsible for imparting color? So the functional groups which contain the multiple bonds. So they absorb the radiation above 200 nanometers due to different transitions, n pi star transitions and pi pi star transitions. These functional groups containing the multiple bonds are known as the chromophores. Examples of chromophores are NO2, NO, CO, C double bond N, C triple bond N, C double bond C, C double bond S, etc. Next, oxochrome. So oxochrome is a functional group. When it is attached to the chromophore, it modifies the ability of the chromophore. So it alters the wavelength at which the chromophore absorbs and also the intensity of the absorption. So this is as such do not absorb the radiation. The functional group with non-bonding electrons that do not absorb radiation in near UV region, but when it is attached to the chromophore, it alters the wavelength. Examples of the functional groups which are oxochromes are OH, NH2. Benzene is unsaturated compound. Oxochrome, here oxochrome is OH hydroxyl group and NH2. When OH group is attached to the benzene system, the lambda max or wavelength maximum of benzene changes. Initially, the wavelength maximum of benzene is 255 nanometers. In phenol, lambda max or wavelength maximum value is 270 nanometers. And in aniline, the lambda max value is 280 nanometers. So the lambda max value increases on attaching the oxochromes to the chromophore. So I'll repeat the definition. These are the functional groups when attached to the chromophore, modifies the ability of the chromophore to absorb the light. So alters the wavelength. So here the oxochrome OH group is altering the wavelength at which the benzene absorbs the UV radiation, lambda max value. Bathochromic shift. So bathochromic shift is also known as the red shift. It is the shift of the absorption maximum to longer wavelength. Which causes this effect? So this effect or red shift is caused by the presence of oxochrome or by change of solvent. Examples of oxochromes are OH, OCH3 groups causes absorption of the compound at longer wavelength. Alkaline medium, paranitrophenol shows red shift. So bathochromic shift takes place by the attachment of a group or by changing the solvent. So here in alkaline medium, bathochromic shift is observed. So which causes this shift in the absorption maximum to longer wavelength. Paranitrophenol compound in alkaline medium, oxygen non-bonding electrons are present in the paranitrophenol, but in alkaline medium what happens? Oxygen is present in the form of ionic form, O minus ion. Because negatively charged oxygen, it delocalizes more effectively than the unshared pair of the electrons. So here the lambda max value is 265 nanometers, which is greater when compared to the paranitrophenol. Alkaline medium, the lambda max value of this compound is greater. Next, hypsochromic shift or blue shift. So this is the absorption maxima of a compound shift to shorter wavelength. It is known as hypsochromic shift or blue shift. So this effect is due to presence of a group that causes removal of conjugation or by change of solvent. Similar to bathochromic shift. So bathochromic shift is due to the presence of an oxochrome or by change of solvent. So hypsochromic shift also is due to presence of a group that causes removal of conjugation or by the change of the solvent. So for example, aniline shows blue shift in acidic medium because it loses conjugation in acidic medium. When absorption intensity of the compound is increased, it is known as hyperchromic shift. Next term is hyperchromic shift. When absorption intensity of the compound is increased, it is known as hyperchromic shift. Example is pyridine. The E value or molar extinction coefficient value is 2750. When methyl group is attached to pyridine, 2-methyl pyridine, the molar extinction coefficient value is 23560, which is more when compared to the pyridine. So here the introduction of this group causes increase in the intensity of the absorption. This is known as hyperchromic effect or hyperchromic shift. Next is hypochromic shift. So it involves decrease in the intensity of the absorption. It is due to some groups which are able to distort the geometry of the molecule. So these are 4 important terms. First one is bathochromic shift, hypsochromic shift, hyperchromic shift, and hypochromic shift. Bathochromic shift or red shift. This is increase in the lambda max value. Hypsochromic shift or blue shift, decrease in the lambda max value. Increase in the intensity of absorption is known as hyperchromic shift, and decrease in the intensity of absorption is known as hypochromic shift. Next topic is different transitions in UV visible spectroscopy. There are 4 different types of transitions: sigma star transitions, n sigma star transitions, pi star transitions, and n pi star transitions. We'll discuss in detail. Energy. Here the energy is represented here. So this bonding sigma orbital has less energy. Anti-bonding sigma orbital has more energy. So electrons, when radiation is provided to the matter, electrons which are present in the ground state or low energy state, they migrate to the higher energy level. So low energy to high energy, the migration takes place, or excitation of the electrons takes place from low energy level to the high energy level. So these are the 4 different types of transitions: sigma star, pi star, n sigma star, and n pi star transitions. The highest energy is required for sigma star. Next, n pi star requires energy. Next comes pi star, and least energy is required for n pi star transition. Sigma star transitions. So this transition is seen in compounds which contain sigma bonds. When sigma electron is excited, it enters the anti-bonding sigma molecular orbital. So the energy gap between the sigma and sigma star is large. So it requires a lot of energy, and it is provided by the vacuum UV region. Examples of compounds which show sigma star transitions are methane, ethane, and cyclohexane. N sigma star transitions. So these transitions takes place in compounds which contain non-bonding electrons. So non-bonding electrons are present in ethanol. So for example, ethanol contains both sigma and n electrons. N electrons are non-bonding electrons. Non-bonding electrons are present in the heteroatoms like nitrogen, oxygen, and sulfur. These atoms contain n electrons. So n sigma star transitions and sigma star transitions are observed in ethanol because ethanol contains both sigma electrons and n electrons. So the radiation required for this kind of kind of transitions is 150 to 200 nanometers wavelength range is required. Next, pi star and n pi star transitions. So pi star transitions are seen in unsaturated compounds, and unsaturated compounds containing electronegative atoms show both pi star and n pi star transitions. Examples, so 1,3-butadiene contains double bonds, and so it contains pi electrons. So this compound shows only pi star transitions. Acetaldehyde contains both pi electrons and non-bonding electrons. So it shows both pi star transitions and n pi star transitions. So these transitions occur at 200 to 400 nanometers. So alkenes and alkynes exhibit pi star transitions. Next, aldehydes, ketones, amides, azo, and nitro give n pi star because these compounds contain non-bonding electrons and pi electrons. So methanol and ethanol do not absorb any radiation beyond 215 nanometers. So this is the cutoff wavelength for these solvents. Next topic is Beer-Lambert's law derivation and deviations. Beer-Lambert's law. So what is Lambert's law? And we'll discuss Lambert's law, Beer's law, and combination. Combination of the Lambert's and Beer's law is known as the Beer-Lambert's law. And deviations from the Beer-Lambert's law. What is Lambert's law? So here, when light is allowed to pass through the transparent medium, the medium absorbs some part of the light. So there is decrease in the intensity of the light. So that rate of decrease in the intensity is directly proportional to the intensity of incident light. Lambert's law. So here the definition is given. When beam of light is allowed to pass through a transparent medium, intensity of the light decreases and the rate of decrease in intensity of the radiation with the thickness of the medium is proportional to the intensity of the light. So this is represented like this. Decrease in intensity dI with the thickness of the medium dt is proportional to the I0. I0 is intensity of the incident light. Small t is thickness of the medium. dI is decrease in intensity. Decrease in intensity with the thickness is proportional to the intensity of the incident light. So this can be written as minus dI by I is equal to K into dt. So on integrating this equation, we get minus log IT by I0 is equal to K into T. So finally, this equation can be written as IT by I0 is equal to e to the power minus kt. So this is final Lambert's law. In the same way, Beer's law can also be written. So first we'll discuss the definition of the Beer's law. Beer's law is intensity of the light shows an exponential decrease with increase in the concentration. In simple terms, we can define Beer's law as absorbance is directly proportional to concentration, or decrease in the intensity is proportional to the concentration of the substance. If the concentration is more, absorbance value is more. So the decrease in intensity with the concentration is proportional to I0, intensity of the incident light. So this can be written as minus dI by I is equal to KdC. So on solving this final form of the Beer's law, we get as IT is equal to I0 into e to the power minus Kc. On combining these two laws, Beer's law and Lambert's law, we can write this equation IT is equal to I0 into e to the power minus Kct. So here the final form of Beer-Lambert's law is log I0 by IT is equal to Kct. So here absorbance is log I0 by IT. This formula you have to remember. Transmittance is IT by I0. So absorbance is equal to log I0 by IT, but transmittance is IT by I0. I can write this in this way. Absorbance is equal to log 1 by T. That is equal to log I0 by IT. Molar extinction coefficient. If the concentration is expressed in moles per liter and path length is 1 centimeter, then the absorbance is called as molar extinction coefficient. It is the absorbance of the solution having concentration 1 mole per liter and path length 1 centimeter. Specific absorptivity is the absorbance of solution through a path length of 1 centimeter and concentration is 1 gram per cent or 1 gram per 100 ml. This specific absorptivity. There are some deviations from Beard's law. So Beard's law will hold for a wide range of concentration provided the structure of the colored ion does not change with the concentration. Structure should remain the same. Next, deviations occur if the colored solute ionizes, associates or dissociates. Deviations occur due to the presence of impurities. Deviations occur if monochromatic light is not used. If width of the slit is not proper, also deviations are observed. If there is polymerization, also deviation can be seen. Beard's law cannot be applied to suspension, but later can be estimated colorimetrically. Next part is instrumentation. So the instrument which is used to measure the absorbance in UV or visible region is known as UV visible spectrophotometer. So what is spectrum? If you plot a graph between absorbance and wavelength, then that is known as the spectrum. So here wavelength is taken on x-axis and absorbance is taken on y-axis. The resulting graph is known as the spectrum. Components of the spectrophotometer: source of light, wavelength selector, sample compartment, detector and recorder. So light passes through this monochromator unit. Monochromator contains entrance slit, exit slit and dispersing element. And then it passes through the sample cell. In the sample cell, sample solution is taken. The solution absorbs some amount of light and transmits the remaining. The remaining light reaches the detector. First component is light source. What are the requirements for the light source? It should be stable. It should provide continuous radiation. It should have sufficient intensity. So some examples of the light sources which are used in the UV range are given below. First is deuterium lamp, hydrogen lamp, tungsten lamp, xenon discharge lamp, mercury arc lamp. And these are the sources which are used in the visible range. First is hydrogen discharge lamp. Hydrogen discharge lamp contains pair of electrodes and it is filled with the hydrogen gas under relatively high pressure. So here the working principle is when current is passed through the electrodes, electrons are produced. So these electrons cause excitation of the hydrogen molecules. So in this lamp, hydrogen gas is filled. So the molecules of hydrogen get excited and the excited molecules of hydrogen cause emission of the UV light. So it covers the range of 160 to 375 nanometers. Stable, robust and widely used source, hydrogen lamp. Next source is deuterium lamp. So here deuterium gas is filled in place of hydrogen. So the intensity is 3 to 5 times more. Tungsten lamp. So it provides supply of radiation in the wavelength range 320 to 2500 nanometers. Tungsten is heated to incandescence by the electric current here and the light is produced from the tungsten filament. Small amounts of halogen like iodine is added to improve the intensity. Then it is known as tungsten iodine lamp. Next, xenon discharge lamp. Xenon gas is stored in the lamps. So it contains electrodes. When current passes through the xenon gas, thermal excitation of the xenon gas produces the UV light. So mercury arc lamp, here mercury vapor is stored under high pressure. So mercury arc lamp is used to produce the line spectrum. It gives different lines at these wavelengths. It cannot be used for the continuous spectrum, mercury arc lamp. Xenon arc lamp provides the radiation in this range, 250 to 600 nanometers. Mercury discharge lamp provides the radiation from 350 nanometers to 800 nanometers. Next component of UV visible spectrophotometry is wavelength selector. There are two types of wavelength selectors, filters and monochromators. filters, it is frequently necessary to filter or remove the wide bands of the radiation from a signal. So filters are two types. First one is absorption filters. So this absorption filters contains colored glass. Next, this colored glass filter, this can be used in this wavelength range 390 to 700. Next, interference filters. It consists of calcium fluoride layer between two silver films. This is calcium fluoride layer between two silver films. On both sides of the films, glass plate is present. This is representation of interference filter. Next, monochromator. Monochromator contains three components: entrance slit, exit slit, and dispersing element. Materials of construction for the dispersing element varies. Quartz is used for UV light, normal glass is used for visible, and alkali halides are used for IR radiation. So prism. Prism, when light is passed through the glass prism, dispersion of the polychromatic light occurs. So there are two types of the mountings. One is cornu type and litro type mountings are there. Next, gratings. Dispersing element. This is dispersing element. There are two types of gratings. One is diffraction grating and second one is transmission grating. Next, sample holder. Sample holder in the UV region, for UV region, sample holder is made up of quartz or fused silica. And glass is used for visible range. Sample holder or sample cell is made up of quartz in case of UV, and it is made up of glass in case of visible range. So cleaning is carried out with distilled water, or you can wash the coverts with alcohol or acetone. Detectors. Important question. So there are three types of detectors. One is barrier layer cell, second one is phototube, third is photomultiplied tube. So there are some requirements for the detectors also. We should have high sensitivity, short response type, and also quantitative response. First detector is photovoltaic cell or barrier layer cell. So this detector has a thin film metallic layer which is coated with silver or gold and acts as another electrode. So the diagram is, see, iron layer is coated with selenium. On the surface of selenium, there is a layer of silver. So when light incidents on the silver, electrons are produced. These electrons are deposited on the silver layer. So this silver layer has negative charge and the other side, that the iron layer, has positive charge. So this results in the generation of the current, which is proportional to the intensity of the incident light. So the detector has thin film metallic layer coated with silver or gold and acts as another electrode. It has metal base plate which acts as another electrode. The two layers are separated by semiconductor selenium. So iron and silver layers are separated by the selenium. So this creates a potential difference. When light falls on the selenium layer, electrons are become mobile and are taken up by the silver layer. So there is a potential difference between the silver and iron layer. That potential difference or current produced is proportional to the incident light intensity. Second detector is phototube. Phototube contains evacuated glass tube with photocathode and anode. This is the diagram. This is an evacuated glass tube which contains photocathode and an anode. When light incidents on the cathode, electrons are produced. So that is the principle. The electrons are collected by the anode. When light falls on the photosensitive cathode, electrons are produced. These electrons are attracted to the anode, causing current. So that current is proportional to the intensity of the light. So the materials used for making the photocathode is coated with a layer of cesium oxide or silver oxide. Third detector is photomultiplier tube. So here the principle is multiplication of the electrons produced. So here it contains one cathode, one photocathode, 8 to 10 diodes are present, and anode is present. The principle is when light incidents on the cathode, electrons are produced. These electrons are collected by the diode. These electrons travel towards the diode and they are collected by the diode. So the next diode is maintained at a higher potential, means the potential of the second diode is 90 volts more than the preceding diode. And hence electrons are accelerated towards it and causes the emission of the additional electrons. So here additional electrons are produced from the diode. So from the second diode, these electrons are reaching the third diode. Again here, additional electrons are produced because it is maintained at a higher voltage. So in this way, multiplication of electrons takes place till the electrodes reach the final anode. So several electrons are produced finally. So 10 raised to 6 electrons are produced. So that resulting current is proportional to the intensity of the incident light. So there are two types of the instruments, single beam instrument and double beam instrument. In single beam instrument, from the source light is produced, it passes through the filter or monochromator, passes through the reference cell, detector, amplifier, recorder. So first here, absorbance is adjusted to 0 with a blank solution. And then sample cell, into the sample cell, sample solution is taken and the absorbance is recorded. So that is single beam. In double beam instrument, so here one beam passes through the reference solution and second beam passes through the sample solution simultaneously. So you can see from the source, light is produced and this passes through the filter monochromator to get monochromatic radiation. So this monochromatic radiation is split into two beams with the help of beam splitter. One passes through the reference cell and the other passes through the sample cell. Then detectors and then difference amplifier and readout system. So there are some differences between single beam and double beam UV spectrophotometers. So in single beam, calibration should be done with blank every time before measuring the absorbance. And calibration is done only at the beginning, case of double beam. So radiant energy, radiant intensity changes with fluctuation of voltage. So here the fluctuations do not have much effect on the intensity changes. It measures the total amount of the transmitted light reaching the detector. It measures the percentage of light transmitted absorbed by the sample. So it is not possible to compare the blank and sample together. So here you can do the simultaneously. The double beam, it is possible to do direct one-step comparison of the sample in one path and standard in the other path. In this scanning can be done. So here scanning cannot be done. Means every time it has to be adjusted with the help of blank. Working on single beam is tedious and time consuming and working on double beam is fast and non-tedious. So last topic is applications. So there is single component analysis and multi-component analysis. Single component analysis can be performed by three methods: by use of standard absorptivity value, use of calibration graph, and singular double point standardization. First method is use of standard absorptivity value. Here Beer-Lambert's law is utilized. According to Beer-Lambert's law, A is equal to A 1% 1 centimeter. This is specific absorptivity. B, C. So B is the thickness of the medium. C is the concentration. This is specific absorptivity. This is thickness of the sample cell or path length, B. and C is the concentration. Molar absorptivity, A is equal to EBC. Here E is the molar extinction coefficient. By using this formula, if we know the A 1% 1 centimeter value for the particular substance, the concentration can be determined based on the absorbance. Next, use of calibration graph. So here reference standard substance is required. So 4 to 6 standard solutions are prepared. So 4 to 6 different standard solutions are prepared and graph is constructed between the concentration and absorbance. For the unknown sample, measure the absorbance. So unknown sample, absorbance of standard and sample solution are measured. Absorbance of standard solutions is plotted against the concentration. So 4 to 6 is different standard solutions. For them, absorbance is measured and graph is plotted between the absorbance and concentration. For the unknown, measure the absorbance. Suppose the absorbance of the unknown sample is 0.6. So the corresponding value. This is the concentration of the unknown sample. From the graph, concentration of the unknown sample can be calculated by using this regression line equation. Y is equal to mx plus c. Next, third method for single component analysis is single and double point standardization. In single point standardization, one standard and one sample solutions are used. So for the standard, we know the concentration of the standard and absorbance of the standard is measured. For the test, absorbance is determined. By using this formula, concentration of the test can be determined. Concentration of test is equal to absorbance of test multiplied with the concentration of standard divided by absorbance of the standard. Next, double point standardization. Two standards are required here, standard 1 and standard 2. By using this formula, we know the concentrations of the standards, measure the absorbance of the two standards, and measure the absorbance of the test sample. So from this, concentration of the test sample can be determined. So here C standard 1, C standard 2, and C test. These are concentration of standard 1, standard 2, and sample solution. Absorbance of standard 1, standard 2, and absorbance of the test solution. Double point standardization. Next is multi-component analysis. So multi-component analysis, the important methods used for multi-component analysis in UV spectroscopy are simultaneous equation method, absorbance ratio method, derivative spectrophotometry, and difference spectroscopy. First is simultaneous equation method. So if the sample contains two drugs, both are UV absorbing, X and Y. So first you determine the lambda max of both the drugs. The lambda max of X is lambda 1, lambda max value or wavelength maximum for the drug Y is lambda 2. So determine the lambda max for both the drugs and they construct the graph like this. So measure the absorptivities of X at lambda 1 and lambda 2. So denote them as AX1, AX2. Determine the absorptivities of Y at lambda 1 and lambda 2. So here lambda 1 is, this is lambda 1, this is lambda 2. Lambda 1 is wavelength maximum for X and lambda 2 is wavelength maximum for Y. At lambda 1, determine the absorptivity of X and lambda 2 also determine the absorptivity of X. Denote as AX1, AX2. So absorptivity is nothing but absorbance divided by concentration multiplied by path length. Absorbances of the diluted sample at lambda 1 and lambda 2, A1 and A2. So sample solution is diluted and it is at lambda 1 and lambda 2 absorbances are measured. The absorbance values are A1 and A2. Let Cx and Cy be the concentration of X and Y. So the absorbance of the mixture is sum of the individual absorbances of the X and Y. So sample contains both the drugs. So the absorbance is sum of the absorbances of both the drugs. Absorbance of the mixture is sum of the absorbances of both the drugs. So by solving these equations, finally we can derive this formula Cx. This is the formula for Cx and this is the formula for Cy. So if we know absorptivities of X and Y at lambda 1 and lambda 2 and absorbances of the diluted sample at lambda 1 and lambda 2 represented by A1 and A2, capital A1 and capital A2, we can determine the concentration of X and concentration of Y present in the mixture, provided you have to calculate the AX1, AX2, AY1 and AY2 values. Next, absorbance ratio method. So it's similar to the simultaneous equation method. So here isospecific point is used. Here lambda 1 is the isospecific point. Lambda 2 is the lambda max of one of the components. So it is also used for the assay of two components in a mixture. So here absorbances are measured at wavelengths, two wavelengths. One is the lambda max of one of the component. So in the diagram, you can see this is the lambda max of one of the component, and this is the isoabsorptive point. Means the wavelength at which both the drugs show the same absorbance value. That is isoabsorptive point. So at this wavelength, this is the second wavelength to be considered. So determine the absorptivities of X and Y at lambda 1 and lambda 2. Represent them as AX1, AX2 for X and AY1, AY2 for Y. So by using this formula, final formula, this formula, Cx can be determined. So here we know what is AX1. This is absorptivity of X at lambda 1. A1 is the absorbance at the first wavelength of the mixture. Next, Qm and Qy. So Qm is equal to A2 by A1. Qm is equal to A2 by A1. And Qx and Qy. Qx is Ax2 by Ax1. Qy is Ay2 by Ay1. So these terms are absorptivity of the drug Y at wavelength 1, Ay1. Ay2 is the absorptivity of the drug Y at second wavelength. So you have to calculate the Qx, Qy and Qm, and then Cx can be calculated. Derivative spectroscopy. So derivative spectroscopy, here the normal spectrum is converted to first derivative, second derivative or higher derivative. So how we can convert the normal spectrum into the first derivative, we'll see. See, this is zero order spectrum. This is first order spectrum. And this is second derivative. First derivative, second derivative. First derivative means dA by d lambda. Difference in absorbance divided by difference in wavelength versus wavelength. And this is d square A by d lambda square versus wavelength. This is second derivative spectrum. First derivative is plot of rate of change of absorbance with wavelength against wavelength. Next, second derivative is plot of d square A by dy square, d square A divided by d lambda square versus lambda. Next, difference spectroscopy. So here in difference spectroscopy, the reproducible changes may be induced in the spectrum if the analyte by the addition of one or more reagents, the absorbance of intervening substance is not altered by the reagents. So these are some of the criteria for difference spectroscopy. So the absorbance of the compound in acidic medium and basic medium. Here, this is the spectrum. So the spectrum is drawn between wavelength and absorbance. So this is the compound in acidic medium. Spectrum of the compound in acidic medium. And this is spectrum of the compound in basic medium. So this is difference between these two values, this spectrum. So the simplest and commonly employed technique for altering the spectral properties of the analyte is adjustment of pH by means of aqueous solutions of acid, alkali or base. So So that is the method for difference spectroscopy. Thank you.